In this lab, we are studying Newton's second law by applying it to the motion of an object falling with a non-constant velocity. I have dropped the ball from wrist, and I observe that the velocity increases as the object falls. My objective is to understand and predict the motion by using Newton's second law to create a computational model for the motion and compare the model motion to my experimental motion. I found that my first model without drag underestimated the position of the ball with greater error as the time increased. My second model with drag was more accurate, with minor discrepancies towards the beginning when the motion started, which I will discuss later, but for the most part it was a very accurate model for predicting the motion. My experiment setup consists of the ball sitting on the origin of my chosen coordinate system, and it falls along the negative y-axis, with the y-axis being the vertical axis and the x-axis as the horizontal axis. I have used a meter stick for the calibration stick, and it sits in the background of my video. As we can see, the ball's velocity is increasing, as shown in the graph with the curved line representing non-constant velocity, and if you analyze the data, the velocities are increasing up until the last 3 frames, where the velocities max out at negative 5.121 meters per second. The most important part of our computational model is being able to correctly set up Newton's second law. We use it in the update velocity form. We know the initial conditions from the tracker data, so we were able to fill in the initial velocity of 0 and the mass of 1.81 kilograms. The final part to completing the equation is to figure out what the net force acting on the ball is, and Fnet has 2 components here, the weight force and the drag. First is the weight force, and I have updated the equation for the weight force accordingly. The weight force is the interaction between the Earth and the object, and is modeled by the equation W equals negative mass times gravity times J hat, which is written in code as shown. The second force acting on the ball is the drag force, which is the force that begins to kick in to slow the motion down, and including the drag force helps to make the computational model more accurate than it was before. The equation for a drag force that's direction is always opposite to the direction of the object's motion, and whose magnitude is proportional to the square of the object's speed is shown in code here. E was calculated through trial and error, making sure the ending position printed by the code matched the one in the tracker data. Looking at the actual data, when the proportionality constant is 0, there is no drag. We can see that the object continues to accelerate until the end of the time interval. However, when drag is taken into account, we can see that the ball begins to slow down when the drag force, as seen by the blue arrow pointing up in the last few frames. Now that we have collected both our model and experimental data, we move on to comparing the 2 sets of data. After collecting all the data into one spreadsheet and setting the model and the experimental data side by side with the times, I have created this graph, which represents the motions. We can see that the line that represents the model with drag is more accurate, although discrepancies still exist. The reason I found for the discrepancy is that during my experiment, the ball remains at rest for a little bit, as opposed to the motion starting right then. This is the cause of the difference, since the model is predicting as if the ball were to go into motion right then, whereas in my experiment there is a delay before motion begins. Since terminal velocity is achieved when the net force acting on the object is 0, meaning there is no speeding up or slowing down of the object, terminal velocity is achieved when the drag force is equal to the weight force and the velocity is constant. Terminal velocity is only possible in the model with drag, since drag force is needed to cancel out the weight force and create the net force of 0. Terminal velocity is seen in the end of my experimental data when the velocities will equal negative 5.121 meters per second. It is also seen in my model data in this graph, where I have extended the time the model runs in order to show it better. The orange line, which is the model with drag, starts to straighten out, whereas the blue line, showing no drag, continues to curve. Even if the initial velocity was not equal to 0, in my case, I chose to make it equal to negative 3 meters per second. The terminal velocities would still be the same for both, as we can see on this graph by the lines showing the different velocities converging. The terminal velocity is the same for both because terminal velocity is dependent only on the drag and the weight forces, which are the same in both cases.